All right, this is Unit 3, Lesson 5 of our calculus class. Unit 3 is called Implicit Differentiation. And we also threw in inverse trig functions and this lesson. And so this lesson right here really could have been thrown in earlier. We're just kind of finishing up or tying up some loose ends for derivation. This is the last lesson for this unit. So after this, we'll kind of switch gears and look at more applications of derivatives. So lesson 5 here, derivative of e and natural log of x, round 2. What we're going to do is we're going to talk about how to use chain rule with these derivatives. Okay, straight to examples. So at first glance, it looks super nasty, but it's actually not that bad. So if you have y equals e to the power of that long polynomial, 3x to the power of 4 plus 6x cubed. If we want to derive that thing, the parent function is e to the power of x, and the derivative of e to the power of x is itself e to the power of x. And since we have, instead of x as the exponent, we have a polynomial, then we're going to use chain rule. So the derivative of e to the power of this polynomial is going to be itself times the derivative of the polynomial. So the derivative of 3x to the power of 4 is 12x to the power of 3. And the derivative of 6x to the power of 3 is 18x to the power of 2. We'll multiply this polynomial by our original function and call it our derivative. Multiplication is commutative, so we could put the polynomial in front of the e if we wanted to. If we put it in front, either way, we want to make sure we put brackets around it. That way e gets multiplied by the whole thing and not just one of the terms. Okay, so the second example is pretty analogous. The derivative of e to this polynomial is itself times the derivative of the polynomial exponent. Okay, so natural log derivatives. Remember that the parent function natural log derivative is just 1 over x. So because we have a function inside of the natural log, we'll do the derivative is 1 over that function, and then we'll multiply that fraction by the derivative of that function. So the derivative of 4x to the power of 6 is 24x to the power of 5. And so if we put those fractions together and simplify, we get 6 over x here. Here we get 1 over the inside function times the derivative of the inside function, and we write that one out. We could simplify that. We could pull out, we could pull the negatives out, negative 1 over negative 1. We could pull x squared out. If we did that, we'd be left with 15x squared plus 3 over 3x to the power of 3 minus x. But again, this is calculus, not algebra, so I'm not super picky about simplifying. Although I would admit it makes it harder to grade quizzes, but it's cool. Okay, so how about this one? We've never talked about deriving log functions before. So to derive a log function, we're really just going to use this workaround here. And it's based off of the log property that if I take log base b of x and split it up as log base a of x over log base a of b, I can really make a whatever base I want it to be. And I want a to be a base of e because I know how to derive the natural log of something. So I'm going to take my log, make it a quotient of natural logs, and then I can derive using natural log rules. Okay, that's what we're going to do. So if I derive y equals log base 2 of our polynomial, I'm going to rewrite this first before I derive anything. I'm going to rewrite this as y equals the natural log of our polynomial divided by the natural log of our base 2. Okay, so now we have in terms of natural log. The natural log of 2 is just some constant value. So I'm gonna separate this fraction up as 1 over natural log of 2, a constant value, times the natural log of our polynomial. So when I take the derivative of this thing, this constant will be part of the derivative. It's just going to remain. So I can really just kind of tack this on at the end and just take the derivative of the natural log function, which of course is a chain rule. So I'll have 1 over this polynomial times the derivative of this polynomial. And we could stack this up. We could put this polynomial on top. We could put brackets around the denominator polynomial and slap a natural log of 2 in front of it. But we don't have to. Oh, I did it right here. Here it is. If I did want to simplify this, I could pull an x term out of the top and the bottom. That's about it though. Okay, takeaways. We can use chain rule and some log properties to work with more complicated e and log derivative functions.